Thank you guys, Mr. G. We're going to try to finish out this chapter. So this will be the last lecture for the year. Today, the first thing I want to talk about is where this energy comes from, where the energy comes from to move these tectonic plates, to move these huge pieces of lithosphere. And then the second thing is I want to talk about some of these different plate boundaries and what happens at these different types of plate boundaries. So, okay, this is the one thing that Alfred Wegener, again, like we said, didn't have the ability to answer. He did. I mean, the technology just wasn't available then. Okay, as we kind of progressed into the 1950s and 1960s, scientists gained a much more complete or a much clearer picture of where the plates get this energy to move. Okay. Scientists believe that there are three different ways that these plates, or three different sources of energy for these plates, okay? And this is not anything that's out of the ordinary. It's not some bizarre force or something like that. It's very, very rational, okay? So the first one is called ridge push. What ridge push basically says is that at the mid-ocean ridges, because they're at a higher elevation, gravity is going to push the plates down those ridges. So they're sitting on top of the asthenosphere. The asthenosphere is kind of like in that putty-like state. Okay, so imagine if you were on a sliding board that had like honey on it, okay, and you were on the top of the sliding board. Would gravity eventually pull you down to the bottom? Yeah, absolutely it would, but it would take a very long time to do. And that's why these plates move so slow. When we're talking about plates move in terms of like centimeters per year, okay? Anywhere from probably 2 to 10 centimeters, which would maybe be a maximum of like 4 inches. So they're not moving very fast, okay? We said again, the asthenosphere moves about the rate at which your fingernails grow. So, that obviously makes sense, but that's basically what ridge push is, okay? Gravity is that driving force. So, again, the mid-ocean ridges are higher. The plates are on those mid-ocean ridges. Gravity is going to slowly pull them down those ridges, and that's what's going to cause the mid-ocean ridges to open up too also, okay? Next one is called slab pull. Slab pull has to do with buoyancy. So what happens is at the trenches, when one of these plates starts to sink because of its density, because it's more dense, it's actually going to start to sink and pull the rest of the plate with it, okay? And that's what slab pull is. It would be very similar to if you had a brick and a rope tied to that brick. If you threw that brick in the water, the brick would sink, obviously, and it would pull the rope with it, okay? Slab pull is when one of these huge slabs of tectonic or a plate or lithosphere gets into the asthenosphere, and because it's more dense, it starts to sink and then pulls the rest of the plate with it. And then the last one scientists think is possible is convection. Okay, you remember we talked about convection a little bit before. Convection is the circular flow of matter, and you can kind of see it here. As matter gets hot, it rises, it cools, becomes more dense, and sinks. Okay, inside the Earth, scientists have identified what they call these convection cells. Okay, so these convection cells, as this matter swirls, it's going to cause the tectonic plates to kind of move and slide also. Okay, so you can see here's slab pull, here's ridge push, and here's convection. If we put all three of these mechanisms together, scientists believe then that that's the source for this energy, okay? Now, the last part of this chapter deals with this, okay? When these tectonic plates interact with each other, we're going to see crazy things happen, okay? So tectonic plates can interact with each other in three different ways. They can come together, they can converge, okay? They can move away from each other, which is to diverge, or they can rub against each other, okay, which is called a transform boundary. So depending on the type of boundary and the type of crust that's involved, we're going to see some interesting things happen, okay? And this is just another picture, okay? So whenever a plate touches another plate or interacts with another plate, we call that a plate boundary, okay? Like we said, there are three different ways that they can interact. This is a picture of the first one. This is an example of a divergent boundary. So at a divergent boundary, the plates are going to move away from each other, okay? You can see here in this animation, when they move away from each other, that's going to create a crack. Magma is going to be able to rise. And what we're going to see is new crust being created at divergent boundaries. The mid-ocean ridges are all examples of divergent boundaries, okay? We're going to see crust being created. It doesn't just happen on the ocean. We can also see this happening on land. It happens in two places on land. One is Iceland, So Iceland is actually on two different plates. It's on the Eurasian and the North American plate, and those plates are pulling away from each other. So Iceland is sometimes called the land of ice and fire because there's a lot of volcanic activity that occurs there. Okay. The Great Rift Valley in Africa is another place where we see this happening. And it creates a very unique ecosystem there. Okay. This is an example or a picture of a transform boundary. Okay. Transform boundary is when two plates slide in opposite direction. You can see this is a very famous example of a transform boundary, the San Andreas Fault. So, and if you think about the San Andreas Fault, you think about California, hopefully one of the things you're thinking about is like earthquake activity, okay? And that's one of the things that happens here. We're not seeing crust being created, we're not seeing crust being destroyed, but sometimes what we see is like earthquakes happen here at these transform boundaries, okay? The last boundary is a little bit more complicated. The last boundary is a convergent boundary, okay? And a convergent boundary is when two plates collide with each other, but the result is going to be dependent upon the type of crust that's involved. Okay. That's the key. Okay. So you remember we have two different types of crust. We have oceanic crust, we have continental crust. So we can have three different combinations of convergent boundaries. You could have continental crust colliding. You could have continental oceanic, and you also could have oceanic. Okay. So again, the end result is going to depend upon the type of plate that's involved here. So this right here is a picture of the first one. This would be an example of continental crust and oceanic crust. Okay. One of the things you remember, oceanic crust is more dense than continental crust. So when an oceanic crust and a continental crust collide, the oceanic plate is always going to subduct. Where that subduction occurs, it creates a subduction zone or creates a deep sea trench. Okay, that subducting plate oftentimes will melt. If that plate melts and that magma rises, it could create volcanoes like on the surface of the Earth. Where are some places where we see this happening? Well, we see this happening around the Pacific Ocean. The Pacific Ocean is called around the Pacific Ocean, it's called the Ring of Fire because we see a lot of these trenches and a lot of these boundaries. Mount St. Helens is an example. That's a clear example of this. Where we see oceanic plate, the Pacific plate going underneath the North American plate, and it creates a volcano. And that's what this says here, okay? Next is oceanic, okay? So here, what we see again is when these two plates collide, whatever plate is at a lower elevation is going to get pushed underneath, and it's again going to create a trench, okay, a subduction zone. The subducting plate will melt, and oftentimes what it will create are some island volcanoes. Now, probably if I asked you to think of an example, you probably would say Hawaii, but that's not the case. Hawaii is in the middle of the Pacific plate, so it's not at a subduction zone. Hawaii actually formed because of something called a hotspot. Okay, but we do see this again around the Pacific Ocean. Japan is a great example of this. Into Indonesia, we see it through Indonesia there. So there's a lot of the examples of these volcanic island archipelagos that are created because of the convergence of oceanic and oceanic crust. And that's what this says here, okay? The final one, and again, all around the Ring of Fire, you can see that there. Those are all examples of places where we see these trenches, okay? Final is continental, okay? So when two continental plates collide, you can see if there was oceanic crust that's attached, the oceanic crust might subduct, but none of the continental crust is going to subduct. Instead, this is what you see happen, okay? This is where we see uplift occurring. And an excellent example of this is the Himalayan mountains, okay? The Rocky Mountains was an example also, but the Himalayas are still active. We still see this happening there, okay? So these two plates collide, they're going to cause uplift to occur. All right, now, how do we know that these plates are moving? That's really the last question, okay? So scientists basically use GPS to track plate motion, okay? Just like they would track the motion like in your car, if your car has GPS or whatever, okay? What happens is scientists put these little things here, I'll show you, that's right here, and I'll go back, into the ground. And this is basically like a GPS receiver. And what this thing does is it constantly is in communication with satellites, okay? If you know, GPS stands for Global Positioning System, by the way, too, okay? It's a network of, or a series of 24 satellites. And those satellites use a triangulation method to kind of pinpoint where your location is. You can see that there has to be enough satellites to cover the entire surface of the Earth, okay? So what happens then is the first satellite would kind of, give a rough estimate of where your location is by drawing a circle. It would say you're somewhere here. Satellite number 2 would do the same thing, okay? And once these two circles intersect, then these are the two places it's saying that that person could be. Okay. Once the third satellite comes in, it draws a circle also. Now the intersection of all three of these is going to pinpoint your exact location. That's how that triangulation method works. Okay. This next picture, this next map does an excellent job of kind of showing how these plates are moving. So all of these represent places where scientists have those GPS locators. Okay. And what those GPS locators do are they're constantly relaying information. So then what scientists are able to do is, again, these are just vectors. So they're showing the magnitude and direction that the plate's moving. You can see the North American plate is kind of turning a little. Okay. You can see that the Australian plate is plowing very quickly into the Pacific plate. And then you can see how this plate, the Eurasian plate, is kind of spinning a little bit towards the Pacific. So what's kind of interesting to think about is that the Pacific Ocean is actually like being consumed. It's actually shrinking. Okay. We're actually moving closer to Asia, and on the opposite side, really farther away from Eurasia. So at some point, you know, these pieces of land are probably, or pieces of crust are probably going to collide with each other. Same here. You can see that the African plate is kind of sliding very quickly towards the Eurasian plate also. Okay. And then we're here, very little movement on the Antarctic plate, but then you can kind of see a little bit of rotation, a little bit of northerly movement in, in the South American plate. Okay. All right, guys. That's the end of the discussion. So again, I hope everything is well. If you have any questions from here on out, definitely make sure that you email me. Still getting a couple emails. That's fine. And I'll definitely make sure I answer them. Monday is kind of our last official day. So you want to make sure you have everything turned in by Monday. But then grades aren't going to go out till like a week after that. So I'll still be available for any questions or anything you have. So thanks, guys.